All right, everybody. Today we have Yoav Artzi, who's here, and I could give you this really cool bio about his PhD, University of Washington, his time, as being a professor at Cornell Tech and a bunch of awards. But instead, long time ago, when I was a grad student and Yoav was a grad student at the same time, we both decided that we should work on grammar, and I decided that we didn't need semantics. What is meaning? Who cares? And Yoav was like, that's ridiculous. Like, what's the point of language if you don't have meaning? And so as we walked around the random streets, I think one time in Austin at like a workshop arguing about this, he said something to the effect of, you'll realize I was right. So,
didn't say that.
Now it was nicer than that. It was nicer than that, but that was the undertone.
It was very hot.
It was very
hot.
It was very hot. And so then, as many of you know, after I finished working on syntax, I then pivoted, and then I've only done things with meaning and grounding ever since. So, in a long way of saying, basically, Yoav was, in fact, right. So, whatever he talks to us about today is probably something that we should, take heart as actually being important and meaningful, because learn from my mistakes. So, with that,
thank you,
Yoav.
Actually, so I thought how I'm going to start. I thought I'm going to start by thanking Jonathan for not bringing up any embarrassing moments from our PhDs together, because he is now more mature as a faculty, and clearly I didn't prepare right. But one thing to be said, it's only happened. Jonathan only moved to semantics after he solved syntax.
That's right.
Okay, so thank you everyone for coming. I'm going to talk today about interaction and natural language learning. So this is not working. Okay, yeah, now it's working. So the kind of like the underlying, the guiding principle of the two topics I'm going to talk about today is that language is inherently an instrument of interaction, and it's actually acquired through this interaction. And this is very, very different than how we talk about language acquisition in NLP. Because we do either supervised learning, or more recently, we do self-supervised learning, but interaction doesn't even factor in any of these things. And thinking about interaction really have dramatic implications for how we think about how we do machine learning and how and what kind of applications we can deploy with language. Okay, so this is something to keep in mind. The talk will be divided into two parts. In the first part, I'll talk about the work of my PhD student, Noriko Kojima, and focusing on collaboration with natural language coordination. I'll describe abstractly the kind of scenarios we're interested in, and then I'll instantiate it in a serial bar, which is a game-like collaborative environment that we built in our lab. And then I'll focus on how we can learn to generate instructions in these kind of scenarios and improve this process, the generation of the instructions through interaction with users. In the second part, I'll talk about Little Jim, which is the work of my PhD student Ann Wu, which is, as the name suggests, it's a little language conditioned RL benchmark that we are pushing out in the next few days. Okay, so let's start. So in the first part, the kind of interactions that we are interested in, I have two agents. You can think about it, for example, as a human user and a system. And most importantly, both of them act in the world. So they collaborate together by doing things in the world to complete tasks. And they coordinate using natural language. So you can think about this as an abstraction of the system can be a robot in a physical environment working along together with a human, or maybe the system is a virtual agent collaborating with a human in a kind of like a structured software environment or a game. Okay? Now, something that is very important in this kind of environment and arises from the fact that both of the agents act in the world is this ability to dynamic delegation. So if you would think, for example, a human user might give a system instructions, and kind of like observing how the system executes these instructions, it can decide that maybe the system doesn't really know how to do what I ask, so I'm going to ask it to do other things. But because I'm acting in the world, I can do what is it I intended myself, and we can still accomplish the goal together. So I can dynamically change how I delegate tasks to it. And this kind of dynamic delegation, in turn, is what enables this kind of system to support continual learning, where the system learns through the interaction with users. And you can think about various forms of learning signals for this kind of, for learning through these interactions. So for example, you can think about explicit feedback, where, for example, a human gives instruction to a system, and watching in real time how the system executes the instruction, it can start saying, oh, now you're doing good, and then when the system deviates and starts doing really bad stuff, can give it negative feedback. So very simple feedback and kind of like that happens in real time during the interaction itself. There are also more implicit feedbacks, for example, by observing the behaviors of the humans. So for example, if we flip the scenario, now the system gives instructions to the user. The system has some kind of an underlying intent that it wants to communicate to the human, like bring me a banana. And then it takes this intent, put it through its state-of-the-art language generation model, and outputs hand me the apple. Clearly, it doesn't really know how to generate the instructions correctly, but our collaborative human that is trying to help it, in this case, what they're going to do, they're going to bring an apple. The system can compare what the humans did to its underlying intent and realize that it didn't really relay its intent correctly, right? And maybe it can use this in order to actually improve how it's taking this intent and mapping it into natural language. Okay? Okay, so serial bar is a collaborative environment that instantiates this kind of collaborative interactions. There are two agents collaborating in the environment. They both act in the world to complete tasks together. And there is a unidirectional natural language instruction where one of the agents gives instructions to the other. Okay? So this is a relatively complex scenario, but it's also in some ways very scoped. So for example, it doesn't include a full-fledged dialogue with bidirectional interaction. And the reason for that is that so we can actually try to think about it in a more principled machine learning way and develop algorithms to deal with it, kind of like taking one step at a time towards a more kind of like the longer term horizon. Oh, what do I have there? Sorry. I can't close that. OK, it will stay. OK, so this is the serial bar environment. This environment includes different elements that are spread around in kind of like this spatial 3D environment. We have, for example, different props like windmills and houses, different types of terrain like mountains and lakes and roads, different cards that are distributed randomly in the environment. And these cards have different types of shapes on them, different number of elements, and in different color. And we have two agents that are collaborating in this environment. One of them is called the leader, and the other is called the follower. The leader plans what they do in the environment and instructs the follower, and both of them, most importantly, they act in the world. Their goal in this environment is to pick up valid sets of cards. So if anyone is familiar with the card game set, this is going to look very, very familiar. A valid set of cards in serial bar is a set of 3 cards where each color, shape, and count are unique. Okay? So for example, in this environment, in this specific instance of the environment, a valid set could include these 2 pink bars, these 3 red triangles card here, and the orange square here. So once they select these cards, and they do the select cards by moving on them to change their selection status, this completes a set, and they get a point. So their goal in the game is to maximize the number of points they're getting, and they do this by completing sets. Once they complete the sets, the cards that are part of the set disappear. 3 new random cards appear in the environment, and the game continues. The two agents collaborate, collecting cards together, and they coordinate using natural language. Okay? The leader writes instructions in natural language for the follower to follow. So the leader's role is to plan and kind of delegate tasks and also kind of like collect cards on their own, where the follower role is to just do what the leader says. And there are a number of design decisions that we implemented inside Serial Bar that are there to encourage collaboration. The first one is that there is an observability gap between the two agents. The leader sees this top-down view, top-down view, what we see up here, without, of course, the occluding text boxes. So they know where all the cards are, and they know what the follower is doing as well. They see everything. The follower, on the other hand, they see a first-person view from their perspective. And the leader actually has access to it. It appears here at the bottom right from the leader's view. But this is all the follower is going to see. So what this means is that the follower can't just go rogue and they collect sets on their own. Because if they do this, first of all, their planning is not going to be optimal because they don't see the locations of all the cards on the board. And second of all, they're very likely to sabotage what is the follower is doing, because they don't know what the follower is doing unless accidentally the follower passes in their field of view. There is also a capability gap in Serial Bar. So the two agents, they move in turns, alternating between another with limited number of moves per turn. The follower has many, many more moves per turn. So what this means is that the leader really wants to use the follower. They have significantly less moves. They can do much less. If they want to maximize their score and get anything done in Serial Bar, they really have to take advantage of the steps the follower has. So the leader can't just go on their own and forgo the follower and the communication. OK, so let's look at like a snapshot interaction from Serial Bar. This is a game between a human leader, that's the colorful figure here at the top, and a model follower. So this is a machine learning model that maps leader instructions into follower actions. So the first thing that they're going to do is the leader is going to kind of plan the sets that they're going to collect, and they're going to collect exactly the set that I showed in the previous example: the two pink bars, the orange square, and the three red triangles. So the first thing that the leader is going to do is going to it's their turn, so they're going to move and collect the card that is next to them, and then they're going to write an instruction. So the first instruction they write to the follower is turn around and get the red triangles next to the mountain. So they want to collect that card there that is just above here that is currently outside of the follower perspective, field of view. So they send these instructions, and because they can buffer multiple instructions, they also ask, then get the orange card, sending the follower from their perspective to the card there at the top to complete the set. The leader will then end their turn, and now it's going to be the follower turn. So the follower, the model in this case, turns around, follows the first instruction correctly, and collects the first card. It will then complete the instruction and move to the next one. It still has several steps within its current turn. But something you can see is that the leader instruction was a bit ambiguous in this case, because it didn't really take into account that there is another card occluded that is a bit occluded here from the leader perspective, and it also has an orange triangle in it. So the next instruction becomes ambiguous, and what's going to happen is the follower is going to pick the card that it seems like the most salient from their perspective, and this leads to an invalid set. So what the leader needs to do in this case is actually needs to correct the follower. So now the follower turn is over. The leader gives them the leader actually gives them instruction: deselect the card you are standing on, and the leader will end their turn without doing anything else except giving the instruction. The follower model will turn back, turn forward, and then go back again to kind of like to fix some issue of deselecting an undesired card. And now it's the leader turn again. They will give the instruction turn left and get the orange square past the windmill. So much more better specified instruction. And again, the model will starts a bit in the wrong direction, but quickly will correct themselves. Maybe not the most efficient way, but will actually complete the task. OK, so they completed the set, they got a score, and the game continues. OK, so before I switch to talk about how we do study the problem of instruction generation in this case. If there is any question about the setup itself, I'm happy to answer. Yeah.
What does the agent know about the environment? Like if you have, like a mountain next to playground or stuff like that, does it inherently know that the mountain is different, or is that something that's learned through that first person point of view?
So which agent? So the follower, what they're getting, so they're getting a structured representation of the environment, but it's structured in the sense, if you're familiar with like how AlphaGo, for example, encoded states, it's basically this kind of like tensor with channels for different properties. So it doesn't know that a mountain has certain functionality that you can't step into it or something like that. It doesn't know what each things mean. It has to learn that, but it doesn't solve a pixel level problem in that sense. Now the difference between now I'm going to talk now actually about learning a leader model, but the difference between the two models in that sense is that we basically mask whatever is out of the observability cone of the follower when we do a follower model. So the kind of like you can think about it as a tensor with most of it like being zeros. Yeah. Okay, so we studied multiple problems with serial bar, but today I'm going to focus on instruction generation. I believe that when my student was interviewing here last year, she talked about instruction following. I think one thing kind of like that is interesting is that the methods actually are very similar in the sense of like learning objectives and learning approaches. Okay, so what does it mean to generate instruction in serial bar? You're getting an input state from the leader perspective. So this is overhead view because you're the leader. And what you want to do is output a natural language instruction that describes how the follower should move in the environment and what cards it should select or deselect. So the first thing we need to do is we need to do some planning. We need to decide what set the follower should select and what task the leader delegates to them. So to do this, we use the deterministic planner. We are not learning that part of the process. So given a state, we get like this sequence of follower poses that kind of like outline how the leader wants the follower to move in the environment. And what we focus on is the second part of taking this sequence and the world states and mapping it to natural language instruction. So what we want to do is we want to learn a distribution that given a world state that I'm going to use kind of like as a globe and some kind of intent that's a map of how you want the follower to move, we want to get a natural language instruction, a probability over possible instructions. These instructions, they must use the landmarks in the environment because the follower has partial observability, and it must be from the follower perspective, not from the leader perspective, because that's what the follower is going to see. And it must exactly specify what cards are to be selected or deselected. Otherwise, it's going to cause a confusion. And the main research question here is like, can we learn to kind of like to estimate this distribution by observing humans executing instructions that are generated by the model? So think about this. So what does it mean? If we assume that we have a language proficient and collaborative instruction follower, a good instruction will basically allow that follower to complete the task as intended, right? You will do what the system wants you to do. A bad instruction is one of two things. It's either inscrutable, you don't know what to make of it, or it will cause you to do something else that is different from what the system intended. So if we look at what the user did in the environment and compare it to what the system intended them to do, the input to the generation system, we can understand how well the natural language communicates the intent. Okay? Now, this kind of learning signal is very loosely inspired by studying in cognitive science and psychology that show that these kind of signals play some role. They're not the only thing in influencing in human language learning. And there's like these really cool studies, like this, starting from the oldest I'm familiar with is from 1966, that show that feedback in interactions kind of influences convention formation and adaptation. So humans are actually really good at like observing what their interlocutor, how they're reacting, and constantly adapting to it, even in the very short time span. And this was reaffirmed again and again and again. One of the most contemporary studies I'm familiar with is Hawkins in 2020 using reference games. So loosely speaking, this tells us two things. First of all, it tells us that for natural language, there is a signal in observing the interlocutor behavior. And second of all, and maybe even somewhat more important, is that there is this expectation for this learning. So when humans come into a natural language interaction, they expect learning and adaptation to happen. They don't expect a static system that doesn't change. So if you think about it, if we want to provide the the full natural language experience, it has to come with adaptation and continual learning, in addition to resolving syntax, for example. It's the last time, Jonathan, I'm sorry. OK, now this kind of signal, I hope, is understudied in this generation. I'm not familiar with any work that has done this. And it's very different from how we do supervised learning. So think about how we do supervised learning for generation. We have inputs and reference outputs written by humans. In active learning, which has this sense of interaction, so maybe it's more related, we're actually doing something similar. But instead of annotating in advance the entire data set, we intelligently select examples. But then we're asking humans to write reference translations or reference instructions or whatever it will be. In our scenario, the idea is to observe executions of instructions generated by the system. So we never have humans actually write instructions. And this signal is also distinct from explicit feedback. So you can think about explicit feedback. You remember in the thumbs up, thumbs down example very early on. And this is actually what we do for instruction following. This requires you to know what is the underlying system intent. We're never going to expose the user to the system intent. So they can't validate it. They can't give preferences like some work does for summarization, for example. And maybe most important, this is really a natural byproduct of the interaction. So you get this by just being in the interaction with the users. OK, so this is an overview of our learning. Don't worry about what each of the boxes mean. I'm going to parse each of them and then get back to this later on. I'm just putting it here to give you some kind of a roadmap. So the process starts by initializing our model. We start with GPT-2 weights to get some general language proficiency. And then we train with very small amount of supervised data to get baseline performance so interaction won't be complete gibberish. And then we interact with users in rounds. In each round, we have a generation model. This is this probability from which we can sample instructions. And we interact with users and sample instructions to delegate tasks to follower users. From these interactions, we take all the interactions, we construct training data from them in every round, and then we aggregate this data across rounds, and we do contextual bandit training to get a new generation model, which we deploy in the next round, and we repeat this process again and again and again. OK, so what does it mean in serial bars? So human users are going to be the follower. The system is going to be the leader. The users, they only see the natural language instructions. They have no idea what the system intends from them to accomplish. The collaborative goals are really important here because they are really going to align the incentives of the follower with the successful intent communication from the leader. So everybody everybody wants to get the system to work here. The language channel in serial bar is unidirectional. And this is not perfect for this specific scenario because it doesn't allow us to catch really, really bad cases. So think about it like this. If we generate complete gibberish, we would like the user to be able to tell us, I don't know what it means. I'm not going to do anything. So we add a binary feedback mechanism to basically catch this kind of scenarios. OK, so let's look at how things look like from the human follower perspective. So this is what our human users see. They see a first-person observation of the environment from the follower perspective, and they see a box of instructions. So they're constantly giving instructions. The current one that they are given is turn right and go straight past the lake and collect 3 circle cards. So once it's their turn, they're going to start executing it. They're going to go straight past the lake. and then very soon they're going to see the free blue circle card. They are going to collect that, and then they're going to indicate that they completed the instruction. Then we ask them 2 binary questions. One, we ask them about perceived correctness. So we ask them if they perceive that what they did is correct relatively to the instruction. Not to they don't know the underlying intent, and to help them, we give them kind of like a partial observability overhead view of the path that they took in the environment. And then we ask them for grammaticality and if the instruction is well written. For that instruction, both were yes. Then here they get another instruction: turn left, grab the black star, and then the 2 green square, then the green squares. You can already see that something is a bit messed up with this instruction. So they start. They move in the environment, they see a black star, they will pick that one up, and in the distance you can already see the green squares, so they'll go grab that. Then they will indicate they complete the instruction, but in this case, for perceived correctness, they said no, but it is grammatical, so that's fine. Okay? Okay, so from these kind of interactions, we get, for each instructions, we get a data point, which is a tuple of 5 elements. It includes the world state and the system plan. These are the inputs for the generation model. We have the generated instruction, the output of the model, whatever the state at that time in the learning process. And we record the user execution. So this is the path that the user takes in the environment. And this path and the path and the plan are very simple data structures. They're just sequences of poses of the environment. And finally, we have the answers to the binary questions of the perceived correctness and grammaticality. From this data, we want to compute rewards. And we do this by comparing the system plan to the user's execution. If they diverge, we know that the instruction didn't communicate the intent well. But it can still be the case that the instruction is a good representation of what the user actually did in the environment, if they perceive what they did as correct. So this gives us 3 cases. The first case, if the instruction is incorrect or grammatical, we know it's a bad instruction. We generate a training example where we pair the inputs, the state and the plan, with the output of the generated instruction, and a reward of -1. If it's correct and grammatical, what we know, if it's perceived as correct, and the grammaticality question is also correct, then what we know is that the execution of what the user did reflects the instruction meaning. So we create an example where we pair the world state and the execution as kind of like, we pretend this is kind of like an input intent with the generated instruction and a reward of +1. And finally, if in addition the plan is roughly equivalent to the execution, then we know that the instruction accurately communicates the plan. So we create an example where we pair the 2 inputs with the generated output and a reward of +1. So this gives us a training data that looks like this. We have inputs, state, and pose sequence coming either from the plan or from the execution, an instruction output, and the reward, a binary reward of +1 or -1. And this kind of scenario, this creates basically what is called the contextual bandit scenario, which is really nice because contextual bandits are relatively data efficient. And this is important here because each of these data points involves interaction with users. OK, so why is this a contextual bandit scenario? So the context is the inputs, the state and pose sequence. The bandit decision is the instruction, so we don't assume any autoregressive process in generating an instruction. The complete instruction is a single decision. And the reason for that is rewards can only be computed for the complete instructions once we observe the execution. Now, the advantage of this, and this is something that's very common in bandit learning, is it reduces to something that looks very much like a supervised learning problem, but where the data comes from the interaction with users. And if there is one thing we learned from like the last almost a decade of neural networks, is that we know how to do supervised learning. That's maybe the only thing we learned, actually. Self-supervised as well. OK, so what we do is we use policy gradient. We maximize the reward. This gives us a gradient. And here you can actually see how similar it is to supervised learning that looks like this. Y is the reward. we have a derivative, the gradient of the log probability, where this is the instruction we generated and the post sequence and the state. So positive examples, you take +1 and you substitute the y, it looks exactly like a cross-entropy term for teacher forcing in language generation. It's the kind of objective we know how to deal with pretty well. There is one problem though. If we substitute the y with -1, what we see is that we're going to have a problem, because this loss term is going to explode. Because as the probability goes to 0, log probability goes to -infinity, you can keep optimizing this forever, and the negative examples are just going to take over the loss. So what we do is a very simple fix. We adapt a very common mechanism from the bandit literature. It also appears in RL in recent years, called inverse propensity score. Inverse propensity score is usually used for debiasing data when you're doing off-policy learning. We're using it a bit differently, but it has this. But we use it in the same kind of like mechanism, but for different motivation. So we add this term ly, and for positive examples where we don't have any problem with, we don't want to touch them, ly is just going to be 1. It doesn't change anything. For negative examples where we have a reward of -1, we are going to this is going to be the coefficient. Is going to be the ratio between the current probability of the instruction and the original probability for when we sample the instruction. So what it means, as this p of x goes to 0, the importance of this example is going to decay. And even though it might explode and go to -infinity, it's not going to matter because it's going to be eliminated by the coefficient. OK, so let's quickly put everything together. So we first initialize, and then we deploy our system to interact with users in rounds. In each round, we sample from our model in interaction with user. We get from these tuples of 5 elements. From these tuples, we compute rewards, and we get training data. We aggregate this training data over time. At the end of each round, we do contextual bandit training using the objectives I just showed with the IPS coefficient. We get a new generation model, and we go back to our users to do another round of interactions. OK? OK, for evaluation, we evaluate 2 main metrics. The first one is task completion rate. So this is the task completion rate of the human followers. How often do they do what the system intended for them to do? We also measure earth mover distance between the trajectory the follower took and the system intent, which is also a sequence of poses. So what we want is earth mover distance to go down and task completion rate to go up. And what I'm showing here is like the solid line is the overall performance. You can see the task completion improves from when we start. Humans successfully complete about 45% of the instructions, where at the end it's almost 80%. I'm also breaking it down here according to how many cards they were asked to select in the instruction, where more complex instructions touch more cards. They have multiple goals. And you can see that there's these learning trends where we first start getting better at simpler instructions and only later at more and more complex instructions. Now, there is one very important confounding factor here that should always bother you when there are these kind of experiments with users over time. And this is how much of this is because the users are adapting to our systems. Humans are pretty good at this stuff. So what we do is we take the initial model and we deploy it in a randomized experiment alongside the final model. So the final round, we have the 2 models deployed side by side and shuffled constantly. So users don't know what they're interacting with. And what we see is that actually none of the improvement is coming from human adaptation. Performance remains slightly the same. This is not always true. In our instruction following paper that we are writing right now, about 1/3 of the improvement does come from human adaptation. We also see increase in perceived correctness, and overall the system, overall the team performs better. So at the beginning they have about 4.5 points per game, and at the end they go all the way to 10.4, which is actually really hard to get over 10 points in this game. OK, we have some other results and a lot more experiments. So the binary feedback for the question helps, but it's actually not critical. We can actually learn effectively even without it. There is an interesting language change over time, so the system changes its language. The effective vocabulary, for example, decreases over time under certain learning design decisions, because we have the kind of variants that we are studying. And there's some interesting interaction between the use of negative examples actually almost forms some kind of a regularization term there that maintains a more diverse vocabulary. And the bandit signal, and that may be even kind of counterintuitive, the bandit signal is at least as good, if not better, than supervised signal. So we actually did a comparative analysis with supervised, and you can see over time that the bandit is just almost the same or better. Okay, so before I switch to the second part of the talk, I just kind of like want to put like a kind of like more of an ad. This is something we are going to release very soon. So everything I talked about so far was with the first version of Serial Bar. We worked on it. We worked on creating it for a long time. It was a huge effort, but it wasn't like the best engineering endeavor. And I don't know. I don't think a lot of people can use it outside of our lab, to be honest. So we went and re-implemented the whole game. We hired a game designer to do the graphics, and we hired a professional, experienced developer to re-implement the whole thing. So we have better graphics, we have better interfaces, it's much more efficient. We have all the logic on the server side, so researchers can play and customize the game without actually touching Unity. We have a new mTurk interface. We have an onboarding process, replay mechanisms, data browsers, and much more, just to kind of like make this much more comfortable for people to pick up on it and customizing it and do stuff with it. So this should come in the next few days. We are kind of like finishing bugs, but if you want, I'll be happy to dog food it to any brave soul here. Okay, so. The bandits are great, actually, and when Elaine was here last year, she talked about learning to follow instruction with a very similar bandit signal, slightly better learning objective that we kind of refined since then. And we have initial evidence for improving extractive QA system with the same bandit signal in interaction with users, using feedback from users that are using system. This was with the simulation experiments. Which still kind of like leaves an open problem of how users behave. Humans are always much more challenging. Yeah?
What's the rough order of magnitude for how many kind of human interactions you have per round?
Oh, that's a great point. So each of these rounds, I think, had about 200 games. We have it in the paper. I'll have to get back to you. But it's on the order of thousands of instructions. Hundreds of games, thousands of instructions. OK, if there are any other questions, this is a great time to let me drink and ask them. Yeah?
I'm curious about like the characteristics of the language that was learned over time.
Mm-hmm.
So I guess like the intent would be better distilled in the final model. But do you think that kind of language would also help like models follow instructions?
Yeah, so I've been getting this question and like multiple times, which makes it very embarrassing why we didn't think about it ourselves. I don't know. I mean, I suspect so. I think that so in general, the way we think about language generation and understanding, or to use better terms, kind of like language, kind of like production and comprehension, is very separate in NLP. And it kind of starts to be, I mean, there is some kind of like exceptions, like, Daniel is working on RSA, where this kind of like generation and comprehension and production are embedded together. But in general, they're kind of separate. So I think there is actually a lot of potential to be explored in thinking how these processes interact. I don't really have concrete answers, though. But it's but it's an exciting question. OK, so I'm going to switch gears now. and I'm going to talk about like more kind of like RL-ish stuff. So I'm going to talk about Little Gym. It's a new language conditioned RL environment, which my students promised me will be available later today, but it will happen in a few days. Always tomorrow. So the goal of language conditioned RL is to acquire a policy that is conditioned on natural language input. So very simple. What we want to do is we want to given a state and a language, you want to output an action. It's like this is very common. We study it a lot in instruction following. There is a critical challenge in this kind of scenarios for RL, and this is reward computation. And the reason it's challenging is because in order to understand if you completed an instruction or if if you kind of like modified an environment to fit the language or something, you need to resolve the meaning of the language. But if you knew how to resolve the meaning of the language, getting the policy would be much easier. So there's like a chicken and egg problem here. And this is something that people have been kind of like struggling for a while as they try to think about NLP and RL. And they do different things. Maybe the most common thing is using synthetic language with some kind of like a formal backend representation that allows you to just programmatically compute rewards. This allows to scale very fast and release benchmarks. There is a problem in that because there is always this risk that what's happening is what you're learning is not really about natural language, but just reverse engineering the synthetic language generation procedure. Other thing that people have done is simplifying the environment, or simplifying the tasks. For example, by creating scenarios where there is like a single state that is the goal state. So if you get to that state, everything is great, and if not, then not. So it's very easy, like a binary switch, basically. Now, let's think about kind of like reward computation in this kind of scenarios a bit more. So what we want to do is we want to evaluate if a state that we are giving it to is a goal state. This is like where the language wants us to go, right? And this requires resolving the language meaning and kind of like comparing it to the properties of the state. So what we need, especially in like simulated environments, we need a formal executable meaning representation. If we had that, we could test it against every state that we are getting into. It won't be a problem. This is actually a semantic parsing problem. And semantic parsing is hard. But we do know how to create data sets for it. So we know how to annotate sentences with their formal executable meaning representations. And this is exactly what we are going to do. We are just going to very lazily annotate our way out of this problem in order to create a benchmark. OK? So there are advantages and disadvantages. Nothing comes for free. So the advantages is it basically solves the problem. So we can capture the natural language complexity and nuance. It does not require simplifying the environment or having like one goal state. We now can handle as many goal states as there are, even if they're all kind of equivalent. We can just test against them. However, as anybody that does semantic parsing knows, it requires an ontology, which is a pain to build, and an API for the environment, and annotation. And this is not simple annotation. This is not a kind of like a accessible language task. This requires expertise. We basically need programmers. OK? So this is what we did to build a language interaction and learning gym, or Little Gym. It's an interactive environment based on NLVR, the Natural Language Visual Reasoning Corpus that we released in 2017. We annotate all NLVR statements with Python programs for exact reward computation. And we design the benchmark so we have multiple difficulties by varying the complexity of action spaces and state spaces. So what is NLVR? NLVR is a visual reasoning benchmark released in 2017. And it has this like very rich compositional reasoning because of how the environment is designed and how Elaine at the time designed that really interesting crowdsourcing process. Essentially, from a machine learning perspective, it's a really straightforward problem. It's a binary classification problem where we are given natural language paired with a synthetic image, and we have to say, do these two match or not? So for example, there are exactly 3 squares not touching any edge. With this image, it's true. With this image, it's false. So the simplest machine learning formulation, binary classification, but a really challenging reasoning process because of how this data is constructed. So to go from NLVR to Little Gym, we create an interactive version of the environment. The objective now is to manipulate an image to satisfy a target Boolean value with respect to an input statement. Now, the actions apply to a backend structured state representation, which is not exposed to the policy, and that is rendered into an image. So the state that the policy is observing is an RGB image. Now, just like because of the construction of NLVR, we can actually vary the complexity of the benchmark and create kind of like sub-benchmarks inside it. So there are two types of environments in NLVR, tower and scatter, which have like very different level of complexity in state space and action space. In tower environments, you basically stack blocks in one of like 3 different towers, one tower in the middle of each of the gray boxes. So this gives us 13 actions. We can add a square by specifying its color and in which box we are adding it. We can remove a square from a box, and that will remove it from the head of the tower. And we need to indicate when we complete the execution with the stop action. Total of 13 actions. There's also scatter environments. Scatter environments are more complex because they allow you to add actions, to add objects in any xy coordinate. And now in addition to having just like one squares of one side, we allow to vary the size and the shape. Okay? So we can add, we can remove, and we can stop. The resolution here is 100 on 380. This gives you over 1 million discrete actions. So it's a very large action space for RL. So in order to kind of like to allow some scaffolding, we also have a grid simplification of the environment where we impose a coarser grid, and then we have an underlying mechanism that automatically transfers the actions to the pixel level. So for example, with the 19x5 grid, which we use for our Bayesian experiments, we have 2,600 actions. Still relatively large for an RL environment. Okay, there are also 2 types of starting states in Little Gym. So we can either start from scratch, and then your target Boolean is true, and you have to build the environment in order to satisfy the natural language statement. Alternatively, we can start from an NLVR image, and we're getting a target Boolean value, and we have to modify the environment in order for this pair to be valid. So for example, here we want the instruction to be false relatively to the image. So in this case, what we do is we add a square. So these different variations, they give us 4 combinations: tower scratch, tower flip it, scatter scratch, and scatter flip it, that vary the complexity of the environment. Each statement and target Boolean value, in kind of like RL terms, they form a distinct Markov decision process. And each of these combinations gives us basically thousands of different MDPs to experiment on. Now, how do we get the annotation? So we use a Python ontology of about 66 functions that is based on an enhanced version of the Goldman et al. 2018 ontology that was developed for semantic parsing on NLVR. We hire programmers for annotation, and we use a custom-built annotation platform. So this is how our annotation looks. We give them an image, we give them a natural language statement, and we tell them to use the API on the left to write in Python the meaning of this statement. So they write the code. We have them in the browser the ability to check the syntax, and we also have the ability to validate. Because NLVR has multiple images paired with each natural language statement, we actually hold all but one image as hidden, and when they press validate, we validate against all of them, and they have to pass all the validation. So we don't want it to overfit to the single image they're seeing, and once they're done, they can submit, and we get a Python program. This process gives us about 2,600 programs paired with statements, which is a very nice resource on its own for semantic parsing or program synthesis. And using this program, the reward computation becomes very simple. all we need to do is to execute when we stop, we execute the program on a state. If it fits the target Boolean, we give it a reward of 1. Otherwise, we give it a negative reward. And here at the bottom, we have some kind of a verbosity penalty. OK, so quickly, we did some baseline experiments. We used 2 models here. One that is simpler is just a CNN and a BERT model, encoding the language and the images separately and putting them together through an MLP. And another more sophisticated VILT, which is a pre-trained state-of-the-art transformer model that just jointly reasons about the 2 modalities. We use 2 learning algorithms. So the first one is PPO, which is a very conventional and common RL algorithm. And we also use PPO with something called stop forcing, which basically is going to help with the exploration problem. So it's kind of like, it's a bit of cheating. When you get during learning, when you get to a state that you would get a positive reward, we stop you and give you a positive reward. So the difference that we're going to see between PPO and PPO plus stop forcing is going to tell us how much of this, that there is an exploration problem in this domain. We learn a policy for each of the combinations separately, and we will simplify the action space for scatter with this 19 by 5 grid. These are our results. In blue, it's the CNN plus, the blues are CNN plus BERT, and the reds are the VILT experiments. You can see that there are various levels of difficulty where accuracy on tower scratch is actually really high, even with just with a PPO. While it goes lower and lower as we go, for scatter flip it, which is our most challenging, you really need a stop force, and exploration becomes really difficult there. But overall, existing benchmarks, they give non-trivial performance, but they also leave a lot to be desired. And maybe it's most visible when you compare the reward that our model getting to the reward that an expert gets, that we get by estimating Anne was sitting there and and playing policy. He's pretty good at this. So this is kind of like the upper bound or estimated reward. And you can see that even in the environments where we have relatively nice accuracy, the trajectories are not very efficient. So this leaves a lot to be desired. OK, so let me conclude with the credits to the people who actually did the work and designed many of the slides. So the generation work I described was done by Nori in collaboration with Elaine. Serial bar 1 was implemented and designed by Claudia Yan, and CB2 is by Jacob Schaff, our engineer. Little Jim was built by my PhD student, Anne Wu, with the help of Keontae Brantley, who is currently doing a postdoc at Cornell. So thank you very much, and I'm happy to answer any questions. Yeah.
So in the flipped task, the task is to change the label.
Mm-hmm.
So how do you mitigate against like annotator biases? For example, in NLI, like adding not was a sort of
Adding what? Sorry.
Adding the word not was a simple way to flip the label.
So the annotators don't touch the language, right? Okay. So and when they give us programs, we hold back. So each statement in LVR is paired in the original corpus with between 1 and 38 or 48 images. So we have many images in the backend that we validate against. So this allows us to make sure that they don't just, and they never see these images, right? So this allows us to make sure that they don't overfit the image that they are getting. And as far as the language, there is no modification of the language here. This is an important. So this is, the little Jim is aimed for a language conditioned RL where we hold the language static. We just kind of like wanted to make it like, the way OpenAI Jim made it like very accessible for researchers to analyze in a set of environments. We wanted to create the equivalent, but with natural language. So this is a very light environment as well. It's like it runs very fast. There is a lot of overhead, unlike something like Serial Bar, for example, which is much heavier, or other environments in NLP like Thor. Yeah. No.
For the first part of the talk with the adaptation of the generation models, if I remember and understand right, like there's kind of feedback on each utterance individually, which lets you use the contextual bandit
So,
Repeat the question for the online.
oh yeah. So, let's see. So the question is about if there is a feedback on every utterance for the bandit. So so in the full scenario, when we deploy the full thing, we ask 2 binary questions after every utterance. But if you remove these questions, you actually there is a very minor degradation in performance. There's actually no degradation in performance. There's degradation in the perceived correctness. So users are less happy, but they perform just as well. So the questions are not absolutely necessary. The reason we added and actually, in retrospect, so we actually didn't separate between the questions. We didn't. Our rules are just end and end, looking at the conjunction of the 2 binary values there. So the reason we added it is because we wanted the ability for the follower to say, this doesn't make any sense. And we could have added it in different ways. Ideally, and that's kind of like, the blue sky dream, is like you have more bidirectional interaction. And that would allow you to get rid of these additional feedback. But the bandit signal itself is coming from observing the executions, not from the questions themselves. And we can compute it without them.
If that feedback's kind of delayed, not just for that one particular utterance, do you think is like RL sort of the right generalization of contextual bandit training?
What do you mean delayed?
Like if you have to say like multiple utterances and you don't know whether it was effective until much later on, like
Yeah.
it's giving the person some knowledge that they are going to use somewhere down the road rather than kind of like.
So okay, so the question is like about if we in scenarios where there are multiple utterances in order to specify a task, if it's more like an RL scenario. That's a great question. I don't have a good sense because serial bar doesn't support it. The serial bar is like a single utterance thing. Now, the thing about RL, how it's structured, is it really simplifies reward distribution because you have this like discounting term that you can basically that causes this decay. So if I have 10 actions leading into the goal, I get the reward, then I will decay it. The first action, unless my decay value is like 1, the first action will get the lowest reward for completing this. In natural language, things don't work like this. This kind of like very monotonous increase of a credit, it doesn't work because if I tell you, Daniel, can you make me coffee? And no sugar, please. Then, according to this scenario, no sugar, please will get higher, will get like more attribution of the credit rather than the make coffee. Now, if you went and make me orange juice, then clearly you missed the coffee part. But the discounting in RL it just doesn't really work. It's like we need something more nuanced in order to attribute. In order to what's called credit assignment, which is a really hard problem. If that makes sense. Yeah.
So it seems like for both serial bar and Delegation, they do have like more real-world applications to some extent, right? For example, for serial bar, you think about maybe a person can extract a blind person and they're linked to data. So my question is like, do you see any artifacts or any feature that is specific to this kind of more synthetic scenario? Then when we try to deploy similar method to the more real-world applications?
Okay, that's a great question. So the question is about like the projection of these tasks into real-world applications. So I think that I think in general, let's see. So in general, we all work on proxy simplifying applications. There are very few people, except maybe machine translation people, that work on like real problems in NLP, including myself, except syntax people. Sorry.
There's a lot of syntax hidden in there, a lot of grammatically correct. Just saying.
So I think and that brings us to kind of like this very nuanced question of when you look at a research project, you have to, and when you're doing a research project, you have to ask yourself, am I making unreasonable assumptions that are just hacking this data set? And that's hard to answer, but I think it's something we all have to answer ourselves all the time. So for example, and I don't think we made these kind of assumptions here. There are things that are simplifying things. So for example, serial bar is a lexically simple environment, which means the vocabulary is constrained. And this is important because I'm not Google. I can't now interact with 100,000 people. I can interact with several dozen people or 100 people or 200 people, and so I can get thousands of interactions. Maybe I can get 10,000 interactions. And this really influences how much data I get, which influences the lexical complexity I can handle. Now, you could go and do little gym and hack your way into it and get probably like really high numbers if you kind of, and people actually have done it to NLVR. I just don't think, I just don't really think it makes great research because we need to remember that these are proxies. And so we need as researchers, we have the responsibility to kind of like design our research in a way that as much as possible, it's never possible in 100%, leaves us aligned with these kind of like what we are aiming in the far future. So you know, climbing on benchmarks and just getting high numbers regardless of the method that you're using is, so I guess what I'm saying it's maybe a troubling trend more generally. Yeah.
Your formalism for NLVR reminded me of Jacob Andres' work on like neural module nets for visual question answering, like in 2016, 2017. Like, do you see connections there? Because he also does like a similar thing where you have like a count module and then all this, but he used that to like construct like a module net rather than as like a formalism.
Yeah. So module neural network was basically a way to take structures that we saw in semantic parsing, create neural modules to them, put them together in a dynamic way. So just like you would construct logical forms in like CCG land, and then execute it. So that was the whole inspiration. So, and this is basically writing lambda expressions in Python.
Yeah.
So in a sense, yes, we are not using it. This is not our models. Our models are completely different. But so in a sense, yes. But the reason for that is because it's all coming from this kind of like Montague-based formal logic that drives all the semantic parsing stuff.
I guess my main question was whether you think like using those kind of compositional inductive biases would like improve performance on a task like this, especially since your reward is generated by this world.
Possibly. I think that it's been challenging to make module neural network work on a natural language and its complexity and be like very competitive and effective. One of the baselines that we applied for NLVR when we published the work in 2017 was we ran module neural network. It can get you something above like a random performance, but not tons. So I don't know. I think these models are very elegant. We like them because we like compositionality, and I mean, at least we used to, and the older people of us still do. I count myself among them, but I think I don't know if we know how to train these models to actually do what we want them to do. There's also work that looked at like what these models learn and actually seeing if the models are learning what we expect them. And I think the results have been very, very mixed. So it's tricky. It's like this modularity and complexity. I mean, look at where we are going. Like transformers is basically an MLP that just moves to the left, moves to the right in English, to the left in Hebrew.
One last maybe, and then.
Yeah.
So last question. What's your view on the balancing between exploitation and exploration in terms of your work, and also have you tried other alternative approaches like Bayesian optimization?
So I didn't try. So the first question: exploration, exploitation in my work or in RL?
In your work.
In my work. Okay, so the first part was about exploration, exploitation in my work, and the second about Bayesian optimization. So I didn't try Bayesian optimization. That's the easy part to answer. Exploration, exploitation in my work. I don't know. I think it's really. I don't know. I think it really varies. I would like to think we are doing a lot of exploration. We don't usually tend to sit on problems for a long time. Although Serial Bar has been cooking in the group for like probably 4 years now. But I think it kind of connects to what we saw, what was the question before that we talked about, like proxy to real applications and stuff like that. If you start and benchmarking, if we sit on these like benchmarks and stuff like that for too long, then the results start the result starts to be less and less. They run a higher risk of like being relevant to the real problems that we want to think. I think that's a general thing. So we try to follow problems. But I do think that exploration is one of the most interesting and urgent problems in RL. So, and it's very hard. And I don't think there are solutions. In bandits too. It's kind of like a fascinating problem. Okay.
Yoav will be here